The Earth orbits the Sun relatively slowly, yet even here on our planet, there's no universal clock we can all use as a common reference. Time seems to flow differently for all of us, something Einstein's theory of general relativity predicted. To notice just how weird this connection between speed and time is, you need to watch things that move extremely fast. It's only then that remarkable paradoxes start to reveal themselves. The faster an object ventures through space, the more it slows its progression through the fabric of time, a phenomenon known as relativistic time dilation. So what happens if you travel at the maximum speed? Photons don't have any mass, so they always move at exactly the speed of light, not slower, not faster, and so time doesn't exist for them. Their journey is instantaneous, even though from our perspective, we notice how time goes by as they traverse space. How does this work? Consider a hypothetical scenario where a rocket travels at 99.99% the speed of light. A passenger on board that rocket throws a ball in the direction of the rocket's movement. The velocities of the rocket and the ball add up, something we would expect from classical Newtonian physics. But if the passenger switched on a flashlight instead, the speed of light wouldn't gain any boost. Both the rocket crew and an observer standing on Earth would record the same speed for the flashlight's beam, since this speed is constant and independent of the velocity of its source. But there's a problem. If the speed of light isn't changing, something else should. Time. Now picture this. You're riding a futuristic motorcycle down an incredibly long, incredibly empty road at the speed of light. You decide to look at your reflection in a side mirror, but there's a catch. The mirror is also moving at the speed of light. So how would the light reflecting off your face even catch up? If you can see your reflection, it would appear to someone watching you that the light bouncing off your face is moving faster than the speed of light, which contradicts the laws of physics. However, no reflection would suggest that the speed of light is not constant. In this case, someone standing beside the road would observe the light moving slower than you do, unable to reach the mirror. To avoid these glitches in the matrix and ensure a consistent measurement of the speed of light for all observers, the universe has come up with a few tricks. When an object approaches the speed of light, not only does its time seem to slow down for us, but we also witness the object shrinking in length. Another visual distortion is when a moving object rotates itself, something called the Terrell-Penrose effect. Although, despite the common misconception, it won't gain any additional mass, rather, it will gain kinetic energy. Yet, the weirdest thing of all is that these changes would only be real to us. For a person traveling at a speed close to c, everything would stay the same. They would feel motionless, time would flow normally, and their body would preserve its usual length. To the rocket's passenger, what's outside the cabin window would seem to act weird and transform or distort. There's no definitive way to tell who's experiencing these strange, almost mystical distortions. The absence of a shared objective frame of reference leaves us in a puzzling situation. Since motion is relative, the distinction between who moves and who remains stationary becomes elusive. It's as if each of us wears a unique set of goggles, offering a slightly different version of reality. Unlike optical illusions, time dilation is a real and irreversible phenomenon. As the rocket slows down and comes to a halt, the crew and an observer on Earth can finally compare their clocks and notice the difference. Time is an unidirectional flow pushing us forward. We've already discovered how to manipulate it to progress faster through time. But what about going against its natural course, into the past? If time passes by at its full rate when we're still, and stops at exactly the speed of light, it's only logical to assume that backwards time travel would require reaching superluminal speeds. For all we know, the speed of light is a unified speed limit, both for moving through time and space. The only decision you have is how you distribute that amount of speed between these dimensions. Even today, we can already look back in time. The light takes approximately 1.3 seconds to travel from the moon to our planet. So every time we look at our satellite, we see the way it was a little over a second ago. And if the distance is much greater than that, we can observe a more distant past. So let's imagine that one day we could not only look back in time, but travel there without breaking the cosmic velocity boundary. Scientists have already suggested several hypotheses on how this can be done. One of these ideas is a megastructure called the Tipler cylinder. An infinitely long tube with around 10 or more solar masses squeezed together and spinning several billion times per minute would be able to warp time around it. If in a very distant future we managed to build such a megastructure and flew around the cylinder in a strict spiral course along the direction of its rotation, we'd essentially travel back in time. The closer our ship would get to the cylinder with a density that of a black hole, the faster into the past we'd be able to move. And once we've calculated the time required to spend in this circular movement, we'd simply have to shift the spacecraft away from the Tipler time machine. There's a possibility that, contrary to our understanding, time doesn't have a linear direction. If space and time is one, there may be no difference between then and there, or now and here. According to an idea known as the block universe theory or eternalism, time is akin to a block, and every moment, past, present, and future, exists on equal footing. Just like there is space outside of the visible universe, even though we cannot reach it. If true, the laws of physics in such a universe would allow for traveling into the past, although we wouldn't be able to affect the chain of events as much as we'd like. If the future already exists, then all events are predetermined and inevitable, and people who live in this universe have no free will. Such a world would be full of casualty loops. The casualty loop creates a self-perpetuating closed cycle where events in the future influence events in the past and vice versa. One day, while visiting an old bookstore, you discover a captivating notepad hidden amongst the shelves. It sparks your inspiration, leading you to start writing. With time, you become a renowned author and you decide to create a book. As you walk home on the same day you finish writing it, you pass by an old bookstore and the draft slips from your messenger bag unnoticed. The store's owner finds it and decides to put it on the shelves. This is the same notepad you stumbled upon all those years ago. In this scenario, the loop itself dictates the sequence of events, leaving no room for alternative choices or deviations from the course of events. Some paradoxes in self-contained time loops are even wider.